there we go. Wave 1 plus wave 2 is wave 3.
Yep.
So not really much different from adding numbers, ultimately.
Nope, there's just a lot of them. Yeah.
Right. Infinitely many,
Indeed.
in fact. We did use simple addition on the one direction, but going backwards actually requires calculus.
Absolutely.
But machines do it. Those are exactly sort of the machines that show us, for example, that when you hear a tone from an instrument, that it's composed of particular frequencies of particular amounts, right? And there's a fundamental algorithm, which is very near and dear to me because it's my work, which does this, and it's called the fast Fourier transform, which really underlies sort of all of modern digital technology.
It undoes all of your odd waveforms into their component pieces.
And you can start manipulating the frequencies.
Welcome to Moog Music. We build analog musical synthesizers in the tradition of Bob Moog, who's one of the pioneers of electronic music. My name is Cyril Lance, and I'm a design engineer here. Let's take a little tour of the factory. All right, here we are out on the production floor. This is where we build all our synthesizers and musical equipment. This is where we install all the circuit boards, and Aaron is taking our front panels and putting everything together so that we can start attaching the actual circuit. Synthesizers, as we make them, are electronic instruments, and they can have the form of a keyboard, or they can have the form of a module that can be controlled by many things, pedals, any type of input device. The synthesizers create sine waves. A sine wave is a periodic waveform, and it's really one of the pure waveforms. And sine waves relate to Fourier series, which is a big deal in the kind of fusion of math and sound. Fourier came up with this equation that said any arbitrary function or complex waveform that varies in time can be described with a series of cosines and sines. And this was a very, very powerful mathematical leap at the time, and it really had profound effects on everything we do in terms of electronics, because basically it means that we can break down any phenomenon that we either observe or want to create in nature into a set of sines and cosines. Acoustic instruments typically are limited in their sound capability by the physics of an instrument. For instance, an acoustic guitar can only vibrate in certain ways. When you hit a string, that string can only oscillate in certain modes and excite certain frequency resonances of the cavity of the guitar, or same as a violin or a bass or a flute. An electronic instrument usually has a lot wider variety of expression and tones that it can get. This is close to a sine wave here. I got a single oscillator making a periodic waveform that I can control the amplitude to, which is how loud it is, louder and softer. And the frequency of, if I play an octave down, you see the frequency is how many times per second that waveform vibrates. So in our synthesizers, I can take an oscillator, but I can also change the shape. So you can see that by varying the way the waveform looks, you can get a lot of different types of sounds. This is a square wave, which is a really recognizable sound in electronic music, and this kind of got a buzzy edge to it, and you can see it's got a lot of harmonic content to it, and which means that there's a lot of sines and cosines going out into high frequency. If I break that down and just add the first sine wave, you see that the major sine wave has a period the same as the square wave, but it doesn't sound like a square wave. Now I've added something at twice the frequency. It kind of looks like a molar of a tooth, but you can see it's a lot closer to a square wave now. And as I keep adding higher and higher frequency sine waves, you can hear that it's getting to sound more and more like a square wave. And as you see, the additive waveform, the sum of all those sines, is looking more and more like a square wave. So I keep going. You can even hear the higher harmonics coming up here. Hear way up high. And the higher you go, the closer and closer it gets to a square wave. And now, if you keep adding a whole bunch of them, it sounds a lot like a square wave. So let me turn that off because it gets annoying listening to a square wave like that. So that's kind of a good demonstration of how sine waves and cosine waves, when you add them together in a proper way, can approximate a waveform. We're in a very exciting point in the history of electronic music because there is so much capability. Moog is dedicated to expanding the sound vocabulary, giving musicians the ability to create sounds that nobody's ever heard before. So using these basic math principles, our mission is to expand the vocabulary that musicians and human beings can use to create sounds.
Now that was great. So this really is Fourier analysis in action, right?
I would love to be able to do that for a donut shape, to be able to control exactly what sounds I'm hearing. It's wonderful to see someone who can actually produce the sounds, the frequencies, and the waveforms at the same time.
He really feels like he's really manipulating sines and cosines.
That's great that you could give him a waveform and he can come up with a sound that fits that waveform. It's just wild.
So this discussion that we've been having is starting to resonate with me, for lack of a better word, and resonating back to what we talked about originally with the Greeks. So the Greeks had this mystical feeling. I mean, mystical as well as sort of, sensory, that, strings that were of commensurate length would sound nice together if you plucked them, okay, that they'd be harmonious. And in fact, we sort of see that mathematically they were sort of right with this work. Is that right?
Those frequencies are integral multiples of each other, so you're getting a very nice progression of frequencies mathematically coming off of the string. Yeah.
That's right. Yeah. I mean, so what we're seeing here in the overtones is that so we're getting multiples of frequencies. So we are actually seeing this kind of integer relation between them.
Even though the sound of a violin is coming from a much more complicated shape than a simple string, you still get to have that nice progression of frequencies.
With the instruments, we've been folding in now a little bit of two-dimensional stuff. Is that right?
It's even three-dimensional. Think of the interior of a violin resonating. What are the harmonics of that sort of piece of space? And for me, what it would mean is just there are natural ways waves propagate through that space, and they're associated to frequencies. So to me, the harmonics of the interior of that violin are just those frequencies of the waves that fit nicely inside the violin.
Now, a musician, expert in music, could clearly hear the sounds, off the violin, off the bass, and say, all right, that one's a violin, that one's a bass, even if they were both trying to play A, for example.
Absolutely.
But this very general question of, does the frequency content sort of identify the source is one that you've been thinking about, right?
So a fun thing you can do is take a piece of paper, cut out whatever shape you want. So if you're feeling simple, you could do a square or a disc or something like that. And each of those will have their own harmonics.
Okay, so I've got my scissors and I make these patterns, and now I create drums that look just like those patterns, maybe two drums like that. And so now you're telling me, or we're hoping, in fact, that what I could do is I could thwack those two drums and have a blindfold. You have a blindfold, and you say, oh, that one came from the circle and that one came from the square.
What you could do is you thwack each of your shapes and you write down the frequencies. So it could be an infinite list of frequencies that you're hearing. So you have that sound, and then with those frequencies, those numbers, maybe there's a hope of figuring out which shape you're working with. You can hear things like the perimeter, so how far it is around if you were to walk around the edge of these things. And you're also lucky enough to hear the area.
Well, that's totally
there's
cool.
Stuff you can hear.
All right.
Yeah, and it comes from a really careful study of basically heat analysis for that particular thing. So those are the tools involved.
And going back to Fourier, the man obsessed with heat, so the idea there is that sort of imagining how heat flows on these two shapes, that knowing something about the flow on those two shapes will tell you the perimeter. So it'll tell you the length around it, and it'll tell you the area.
Yep.
And so it sort of speaks to the real title of the kind of work that you do, spectral geometry, because it's really this, total mix of spectral analysis, i.e., thinking about notions of frequency, but meshing them with ideas of geometry. Now, we've been working with this kind of surface, but now we could talk about a closed surface like a beach ball, for example, and you could thwack it just like that, and then there's presumably some analog of everything we've done here, right? And those are the spherical harmonics.
Yep. So one I like to imagine is if you have a sphere and it pinches in along the waist, it kind of stretches out as it oscillates. So it's kind of going up and going out again, going up and going out. So spheres oscillate. That's perfectly fine. They have ways that they'll prefer to oscillate.
These spherical harmonics, that people are now using those things to basically try to understand what the universe sounds like, so that there's this cosmic microwave background which is, vibrating throughout the entire universe, and then understanding that in terms of its harmonics ends up being a deep question related to cosmology and the Big Bang.
And at the small scale, you could use the spherical harmonics to understand how electrons move between energy shells in an atom, for example. So you have orbitals that also use the harmonics of a sphere.
So we have strings, but not quite string theory.
No.
But then we go from you know, electrons, right? And we sort of stop at musical instruments, and then we proceed out to the universe, right?
Yep.
And it's all harmonics.
Yep, it's all there.
Totally cool.
Yeah, it's really cool.
Thanks, Liz.
Yep, thank you.
The Greeks' idea of the music of the spheres, the idea that there must be some connection between music and the workings of the heavens, was based on the mystical numerology of philosophers like Pythagoras. Ironically, even though their explicit declarations of rational orbits analogizing the relative lengths of harmonious strings was wrong, their instinct was correct. While there isn't really a music of the spheres, there is a song of the universe, a steady hum that you hear no matter where you turn your ear, or rather, your microwave detector. That's what Robert Wilson and Arno Penzias discovered in the mid-1960s at Bell Labs. They aimed a radio antenna at the sky and noticed that no matter where they pointed it, they received the same steady microwave signal, which sounded like static. With the help of some Princeton physicists, they realized that this wasn't any old static. Rather, it was very likely to be the spectral remnants of the Big Bang, the leftover vibrations from that initial explosion of densely packed energy that presumably gave us our universe. For this discovery of the cosmic microwave background, Penzias and Wilson received the Nobel Prize in Physics in 1978. The connection to music lies in Fourier analysis, or more properly, Fourier analysis as it is created in the setting of a sphere, which is how we analyze the microwave background. Fourier analysis, as we've been describing it, is about periodic functions, those regularly repeating patterns in time. Fourier showed that these could be broken up into sinusoids of different frequencies. On a sphere, rather than get sinusoids, spherical symmetry leads to functions called spherical harmonics, discovered by the great French mathematician Pierre-Simon Laplace. The secret to the origins of the universe may very well lie in the highest frequency harmonics of the cosmic microwave background. The analogy between the sinusoids and the spherical harmonics is very precise. Whereas the sinusoids end up being the solutions of the wave equation on a line, the spherical harmonics work for a wave equation defined on a sphere. Sinusoids describe waves on a string, and spherical harmonics describe waves on a ball. As the Greeks contemplated the mathematics of music, their ideas went beyond the mere creation of sound that pleases the ear to a model of the outer reaches of the cosmos, where the stars, the sun, and the planets were thought to dance in harmony, to the beat of an inaudible music of the spheres. Today we know that this mathematics of sound goes far beyond sound waves. We've discovered that there are many different kinds of waves. Waves that vibrate in purely mathematical worlds, and waves that surround us in our world, some which we can perceive directly, and others that we can only detect with technology the Greeks never could have imagined, all unified by mathematics.